Okay, so I hope you can see my screen.
We can.
You can hear me as well, so all good. Yeah, thanks for having me, and you're really great to be in this session. Fantastic talks I've seen. And I will be talking today about where we take inspiration from for the robots we developed from biology, and in particular, looking into creating surgical tools, surgical robots in this context. So where do we take our inspiration from? So there are two main areas I would like to, present, and the octopus is definitely a great inspiration for us. Yeah, so very similar to what Cecilia has spoken about. Really, fantastic animal. Has these limbs that have no bones inside, capable to squeeze and go through narrow openings and adjust the stiffness to then also be able to grasp objects such as a bottle or prey. So the other area, going to bio-inspiration number 2, is looking at growing robots, and Tanya has already talked about it very nicely, very nice presentation. And so I give as an example here the eyes of the snail, and you can see how they grow from the tip out of the tissue of the snail. Another example here in this context is the growing of plants, and others have already looked into that. So really taking the point that once the stem is there, it is there, it doesn't move anymore. There's only something happening at the tip, and we have effectively frictionless motion, tip growing. So looking just quickly at the state of the art in robot-assisted surgery, and I'm really, looking here mainly at industrial efforts in creating now systems that can be used for minimally invasive surgery. So the Da Vinci robot is really in the, great example in this context, the market leader. And very clearly what we can see is a robotic structure made from rigid components, as we can see, and they are used then to go through narrow openings into the patient. And we can see very similar approaches across the field. So we have, here the Hugo system from Medtronic, and, again, rigid components, and very similar to this, also from the UK, CMR Surgical with their system. Again, multiple arms that can go into the patient, made from rigid components. And now, so really, we wanted to radically move away from that when we started our StiffLop project, and probably at the time the first large-scale research project suggesting to use soft robots, bio-inspired robots for minimally invasive surgery. And so we developed this system that was made of silicon rubber and pneumatically actuated to help us create tools that could be then inserted into the human body to carry out procedures as required. So we see in the middle the StiffLop manipulator that we developed, and that was below 15 millimeters, so just small enough to go through a trocar port, made of 2 segments, individually controllable, and equipped with a camera at the tip. And we can see it here also going through a so-called trocar port. Inside the patient, in this case, it's just a phantom, and the camera images can be relayed back. And as part of the project, we were also able to actually do a study in a human cadaver. So we can see here the surgeons who were part of the project inserting the device, the soft robot, and here we have a few snapshots of this robot now inside the human body, and we were able to actually do a mock operation for many hours without any problems. So here we achieved 14.7 millimeters, but recent work at UCL by Helge Wurdemann, continuing this work, was able to bring it down to 9.5 and even 7.5 millimeters. We are also extending the work now in our current EU project PALPABLE, where we try now to create soft robotic devices based again on the same principle to palpate tissue inside the human body and use this to for diagnostic purposes. But also very important work was additional work was done during the STIFFLOP project, and here we looked in particular at antagonistic behavior, which is also, of course, in the octopus, and we developed now these inflatable structures. So the air is pumped into these structures made from airtight fabric, and then we use tendon to move them around. And that is at the same time an antagonistic structure, because we have the air going one way, and in the opposite way we have the tendons doing the navigation, but at the same time being also able to compress the air and in this way change the stiffness. So inherently antagonistic. And we can see it here in action. What we also found is these structures had this antagonistic behavior, but they could be also nicely inflated, so they could grow from a very small volume to a much larger volume, the extended form. And then, as you can see here, we use the tendons to move it around in different directions. And this work led then to developing an inflatable endoscope that could go through very narrow trocar ports, again, for example, to explore the inside of the abdominal cavity. Coming now to the other bioinspiration which I mentioned earlier. So going from snails and plants to tip-growing robots, and Tanya has already spoken a lot about this. So here I show now one of our earlier systems, quite large in diameter, capable of growing from the tip, but also bending in different directions. And obviously, other people have worked on that. So here we see work by Elliot Hawkes and Alison Okamura. And here are some examples, oops, going too fast, which maybe I go back again. Sorry, maybe I need to start it separately. So Valdastri, Bergeles, and Rio looking again at eversion robots from different perspectives. And Tanya has already spoken about the magnetic one, which we also see top left. Sorry, Tanya, I don't have any slides about you. Sorry about that. So as you can see, quite some interest in that area. And what I would like to add is one important aspect is now especially if we think about bringing tools into the remote area using those tip-growing robots. One big challenge is to attach these tools at the tip, because the tip is always evolving. So we have introduced the so-called soft cap that allows us to add tools at the tip, and then at the same time also to remain soft and so be able to go through narrow openings. These are larger systems, quite some interest in from the nuclear industry, for example, for these robots for the exploration of radioactive sites. But of course, we are also very interested in colonoscopy. We recently got the funding for a large-scale project. It's an ERC Synergy Grant called EndoTheranostics, and the aim is to develop now an eversion robot that can move forward inside the colon, So very similar to the work that Tanya was presenting earlier. And the idea is through this eversion robot to bring an operating theater to the area of interest and then to operate on the tumor inside the colon. Here are just some initial studies to show how, in principle, we would like to move inside the colon. So we have, an eversion robot inside of a phantom of a colon, moving forward and backwards. I would like to take the opportunity to thank our funders, and in particular ERC for EndoTheranostics and the European Commission for PALPABLE. And also lots of thanks to especially the more junior colleagues who have helped a lot making that work reality. Thank you very much.
Thank you very much, Kaspar, and thanks to all of our speakers in this session.